This is the first of two videos on parsing Lambda expressions. So for the general background, we already implemented a calculator, which can be seen as an interpreter for a simple programming language of arithmetic expressions. And now our aim is to learn how to build interpreters for proper programming languages. And the programming language we start out on is the Lambda calculus. The reason we start with the Lambda calculus is that the Lambda calculus is really the simplest possible programming language. So we define the Lambda calculus here with help of a context-free grammar. Put this in a magenta box. And so the Lambda calculus, the syntax of the Lambda calculus has just three clauses, three rules. One for functions called abstraction, one for applying a function to an argument called application, and a variable. There's not more than only these three operations. And also we can write this down in an even shorter, more compact mathematical notation. So this is the same grammar essentially, with a little e standing in for expressions, and then we have functions, applications, and variables again. So we want to learn how to parse Lambda programs in the Lambda calculus, Lambda expression. So here's one. Here's an example. And so we do this in two different ways. In this first video, we try to understand how the parser, which is generated from this grammar, is doing this. So we have a parser. And this parser is automatically generated from the grammar. And also it takes then as an input the program, the Lambda expression. And what's the output of the parser? It's this horrible long expression which is down here. So let me just fix this. I see now it somehow. Some of the notation here on the program disappeared. So this program in blue is kind of the same as the program in black here. So this is the notation that can be understood by the parser, lambda x, lambda y, x, y, z. So we see here also lambda x, lambda y, x, y, z. And then the first argument to this function is a applied to b, and the second argument to the function is c. So I try to use blue for the more mathematical notation and black for the more programming-like notation. Okay, so in this video I only want us to understand this output of the parser. So it's not that we have to process this by hand usually. So this output looks terrible and it's meant for machine consumption, but as we want to learn how to write interpreters, we need to understand, we need to be able to read this output like this, even if we don't usually want to do this. We need to be able to do it. And the way to check whether you understand such an expression is to see whether you can write this in a more human-readable format as a tree. So this is really a tree here, this expression. And to see that this is a tree, we just process it depth first, left to right, and translate it into a tree. So this is what we want to do here. So I read the first symbol here, which is the E-app, right? And I write it out, and then I've consumed it, so I can delete it now. And now if I go into my grammar, I know that I see that an application has a left branch and a right branch. And then I just continue reading here. So I don't even need to kind of find exactly where to match the parentheses. I mean, that would be one way of doing it. But I can just go left to right here and say, okay, so there's another application. And then again, I have two branches. And then I see that I have an abstraction. So I put the abstraction here. And then next I have an ident and an x. So maybe I should if I'm pedantic, I should put the identifier, the ident here and the x. But actually, I want to just be a little bit briefer here when I write this by hand, and maybe also increase readability. So I just put the x here. Okay, so we've done this, and then on the right, so on the right of the abstraction, so this was, okay, let's just see whether we lose track. So we had an app, an app, and apps. So an app, and an apps. And then apps has two arguments, right? So a variable and another expression. And so now we need to write down the expression, and it starts here with another abstraction. So we have another abstraction here. And then we have the y on the left. And this was the y on the left. And now we have an application. Okay, so let me scroll this up to gain some space. So then we have an application. It was here. And an application has a branch on the left and a branch on the right. So what is the branch on the left? The branch on the left is another application that was here. And then the application has a variable, which is an x, and it has another variable, which is a y. So I'm now here, I've done this, and I've done this. And so I've done all of this. So now I'm going to the right-hand side of this application. So I have another variable and a z. So now I've done all of this. And where am I left? So now I've done all of this here. So I go up again until I find the next open branch. And this tells me that I need to put in another application. So this is here. And then I have two variables. So this is this variable here and this variable here, and they are called A and B. So I call it A and B. So now I've done all of this. And also now what remains to be done. So I've done all of this tree here, and I go up again here, and then I have to have another variable here. And okay, so this is how this horrible looking expression really is a tree. It still looks a little bit complicated, so maybe it's worth simplifying it in terms of our mathematical notation. So let me switch to blue. So now I'm using kind of this grammar and this notation for lambda terms, and I'm drawing the same tree again. So if you see in the mathematical notation, we don't really have a symbol for application. We just write two terms next to each other. So I just draw it like this. Right, so this corresponds to this here. And then I have another application on the left. And then I have an abstraction, and it has an x, and another term which has an abstraction, and it has a y, and then we have an application and an application, and this is the x, and this is the y, and this is the z, and here I have another application, and I have the a and the b and the c. So you see that the tree looks already more friendly in the blue mathematical notation than in the black notation, which is closer to what the machine will actually process. So in the next video, I will show you how to parse this Lambda tree instead of using the parser generated from the context-free grammar by doing it directly by hand from the blue Lambda expression. Thanks for watching.